All right. Well, hello everyone. Good to see you all. I hope you had a nice, restful weekend. This was the same thing in the first lecture as well. There were a lot less people here today than there was in any of the previous weeks, possibly because there was a quiz last week and there's no quiz this week. Actually, before we get started, Ryan F., are you here? There's someone here to give an announcement about something, or that was planning to come today to give an announcement. Okay, so Ryan is not here yet, so we'll wait on that. But yeah, so no quiz last week, no quiz this week, which is probably part of what's going on. So speaking of the quiz, so I don't know, something weird happened last week, because I made like a bunch of silly little mistakes right in a row all around the quiz. So I had 2 typos on the quiz, which is more typos than I've ever had on a quiz. And then I made a video explaining the solution and made a mistake in the video. It was a silly mistake. I put a negative sign where there should be a positive sign, and they got me the wrong answer. All the physics in my video was right, but I made a mistake in plugging into a calculator, which is really easy to do, right? It's really easy to do. So I don't know what was going on last week, but something was, so we're going to try to avoid that in the future, so sorry about that. However, one mistake I did not make about the quiz is getting it graded. The quiz has been graded. We're going to take a break in the middle of our lecture, and we're going to look at sort of the sort of class averages and stuff like that for the quiz. And then, right after we're done with lecture, I will go to my office and I will actually post the quiz grades. Okay, so we have those in plenty of time to prepare for a second quiz. I have been historically terrible at getting quizzes turned around in time, and that's one thing I've been trying to correct. And thankfully, I finally, 1 week is going to be, that's going to be my commitment for the rest of the quarter, is try to get them back in a week. Okay, that's the goal. So anyway, quiz grades are back. I will be getting those back. Like I said, I'll be posting the actual grades when we're done here, and we'll look at some of just the overall grades here in a few minutes. All right? Sound good? Okay. So, again, welcome back. I did not come up with a good title for this one. So, this is a bit of an interesting lecture. Why is it an interesting lecture? Because it's kind of a transition lecture. So we've been spending a lot of time working with sort of energy conservation and learning about our basic kinds of energy. Our basic kinds of energy are thermal energy, bond energy, kinetic energy, gravitational potential energy, and spring potential energy. Right? Those are the 5 energies that we've looked at so far. This lecture really marks a point where we're moving on to describing an entirely new set of systems. Right? So as far as energy is concerned, you've basically learned enough about energy to describe, like 90%, if you just walked out into a forest and just started looking at physics stuff, like 90% of the energies you've got already, right? Those 5 energies will pretty much take care of most of it. But now we're going to start taking those energies and using some of them in a system that is way less what we're used to seeing in our day-to-day lives. And so this is really a transition lecture where we go from talking about energies on large scales to energies on much smaller scales. And so that is a little bit of a weird transition to make. But that's what we're going to be working on this week when we get to the end. But I'd like to start, as always, by just looking at what we did last week, right? Because this stuff especially it's going to come up again. It's going to come up again, and so I want to talk about it a little bit more. So, what did we look at last time? Well, we started by talking about work, right? So work was a thing that up to last week, we just sort of said it was a way that energy can change, right? It's like heat, in that energy sometimes goes in and out of systems, and that causes the energy inside the system to change, or the amount of energy inside the system to change, and one of the ways it can change is work. And we didn't say a lot about what work was or why it showed up until we got to last week. And now we sort of have enough information to understand why we break things up into work and heat, right? Because they're both the same thing, in a sense, right? They're both a way that energy can change, but they're different in one key way, which is that, well, heat tends to involve internal energies. So differences in temperature, right? So you have one thing that's at some high temperature, one thing that's at some low temperature. They exchange some heat and their temperatures change. Work always involves something that's moving. Work always involves something that is moving, right? So while heat pretty much only shows, well, heat involves internal energies usually. Work involves mechanical energies usually, right? And what we discovered is that work involves an object that is moving and experiencing a force at the same time. And the rule is, well, this is not actually the rule. Work is done whenever an object experiences a force while moving is not exactly correct, right? This is only true when the force is pointing in the same direction as the object is moving, or opposite directions. So the example I gave where there's a force and there's a distance but work is not being done is me walking across the floor. Right? When I walk across the floor like this, the floor is pushing up on me the whole time. If it wasn't, I would just fall, like straight to the floor. The floor is pushing up on me all the time, but I'm moving in this direction. So I'm moving this direction. The floor is pushing this direction, so no work is being done. Right? So work is only done, as far as our class is concerned, this is not exactly strictly true, but as far as our class is concerned, work is only done when your force and your movement are in the same direction. Right? And there's this rule for whether work is positive or negative, but I don't want us to memorize it as a rule because I don't think that's useful, right? And this is a general thing in this course. It's very tempting to try to memorize rules, but it's better to understand why the rule is the rule. And I think this is a rule where if we think about why it's true, it's going to be a lot easier to remember than just sort of memorizing it, right? So work is a way that energy can change. And so if you have a system that has some amount of energy, and there's work is, affects the system, and the system ends up with more energy than it started with, that is a case where work should be positive, right? The amount of energy has gone up, so work is positive. And then if you go the other way, and you have a system where that has less energy than it started with, in that case, work would be negative, right? So how do we know if the system has more or less energy? Well, one way, let's just imagine something is moving across the floor, and it experiences some work, and then after the work is done, it's moving faster than it started, right? That is a system with more energy than it started with. And so that tells us immediately the work has to be positive, right? It was going some speed, work was done, it was going faster, it had more kinetic energy, so the work was positive. And then the opposite would also be true. You have an object that's moving across the floor, some work is done, and then it's moving more slowly. That's a case where work is negative, right? Energy is being taken out of the system. And so then the rule becomes, if your force would tend to speed the object up, then it's going to be positive work. If your force is trying to slow the object down, that is negative work, right? But the reason, again, is that, right? Positive work increases the amount of energy the object has. If the only kind of energy that object had was kinetic energy, that means it'd be moving up faster. And so that's how we can remember this. Okay? All right. So one of the reasons that we introduced that is because we wanted to deal with friction and air resistance. Friction and air resistance are, in general, very challenging topics to deal with in a precise way. So I don't know if I mentioned this, but I did not see air resistance in any really meaningful, like deep and sort of quantitative way until I was taking upper division classes in college, right? So this is not a topic that we're going to dive into very much in this course because the math is just really complicated if you want to deal with it precisely. But we do want to deal with it a little bit, and we can think of it a little bit in terms of energy. And there are two ways that we can do it. The first was that air resistance or friction are forces that do negative work, right? Why do they do negative work? Think back to what we said. Air resistance and friction do negative work because they are trying to slow your object down. If you slide this across the floor, it does not speed up, it slows down. It slows down because there's friction between it and the floor that slows it down. And so that friction, we could think of it as doing negative work on the system. But there's another way we can think about it, which is that we can think of it in terms of thermal energy. And the example that I gave, right, was from, the Karate Kid, the rubbing of the hands. If you do that, it will warm your hands up. Why? Because there's friction between your hands, and that friction is converting the kinetic energy of your hands into thermal energy. And this is a general rule. Friction tends to increase thermal energy of objects. So what's another example? Another really great example is brakes on your bike or brakes on a car. Right? In most cases, there are some brakes that don't work this way, but most brakes involve some sort of pad that's, touching the wheel or touching, if you have disc brakes, there's I don't remember what it's called, but the point is there's something touching something else. That fact that they're touching creates friction, and the fact that there's friction slows your thing down and warms up the brake pads. Right? It's the same thing. So there's a transfer of energy from the thermal energy or from the kinetic energy of your system into the thermal energy of whatever is slowing it down. And again, the reality is just in the real world, friction and air resistance show up a lot. The world is, it sort of messes with our models. Our models sort of live in like perfect physics world, or perfect physics math land, like this ideal, like what physics could be. And in reality, the world is not really like that. Friction exists. Although, I think there is a Magic School Bus episode about this. You all watch Magic School Bus? It's a little bit old at this point, but it was really, when I was 6, I thought it was the shit. Like, it was literally the best thing in the world. That and Reading Rainbow with perhaps my favorite person of all time, LeVar Burton. But what's that? It's all about the super. Yeah. There is a Magic School Bus episode about this. I think it involves baseball or something. And they're like they're playing baseball on a frictionless, something like that, right? But in the real world, that doesn't happen. There's friction in the real world. It's just part of life that we have to deal with. We wish we didn't have to, because that would make our math easier, but we just do, because that's the way the world works. Okay, so then we introduce this relationship between potential energy and force. And the reason why might not have been totally obvious at the time. It's going to become more clear why this is when we talk about today's material. But this was the statement. When a system has potential energy, it is usually also experiencing a force. It is usually also experiencing a force. And that force is going to push or pull in the direction that decreases the potential energy. So the example I gave was this object falling. There's a couple of ways to think about why it's falling. And the first one is just, well, we let it go. It has gravitational potential energy. And because of the way that the world works, when an object has potential energy, it's always going to try to convert that potential energy into kinetic energy if given the chance, right? And so when we let it go, we give it the chance and it falls. That's fine, right? That is correct. That is a complete and correct way to describe why an object falls. But there's another one, which is that this object experiences a force from gravity that is pulling it down. And when we let it go, that force... It happens to me. It's happened to me before. So there's a force of gravity that is pulling it down that causes it to fall. Right? Now, again, the details of the force description, we're going to say and it falls, yes. The details of the force description we're going to save for Physics 7b if and when you take it. So we're not going to deal with all of that right now, but we can learn a little bit. Right? In this course, we really need to only know two things. We need to know if you have a potential energy, what direction is the force, right? Is it a push or is it a pull? And roughly speaking, how strong it is, right? And you can get all that information off the graph. It's always pushes or pulls in the direction that would decrease the potential energy. I'm not going to talk more about this because we're going to talk about it a little more GL. And it's going to become really, really important when we start to look at the material, sort of the second big topic in this course that we're going to start looking at today. Maybe it's third. It depends on how you're counting, second or third big topic. Okay. And then we introduce this other way of talking about energy conservation. Now, the thing to note is that secretly these two are the same equation. Secretly this is just a rearrangement of this equation. Okay? It's not that we're introducing a new concept here. It's just we're introducing a new way of talking about it, right? So instead of saying, oh, the total energy is not changing, we're saying the total energy is not changing in a different way. And this is useful for a couple of different types of scenarios that we're going to see, including this thing called the Lennard-Jones potential, which we're going to start talking about in a little while. This is useful, particularly when we're talking about plotting of energies. And plotting of energies we sort of started talking about last week, and we're going to talk about again this week. And then we'll also talk about why plotting energies is important. But again, the key thing here is just that these are the same equation. They're just different ways of thinking about it. So one way that you could solve a problem where this is true is you could use, I don't know if I actually talked about this as an analogy in lecture, but it's if it's in my, where I introduce conservation of energy, the short lecture video, it's that. It's in that video. And the example I use, imagine that you have like 2 cups of water, and you're like pouring water between the cups, right? There's 2 different ways of saying that. One way of saying is that, if you're only pouring water between the cups, then the total amount of water in the cups is not changing, right? And so one way you might say is that the change in the total amount of water is 0. But the other way that you could say that is you could measure the amount of water and say the total amount of water in the cups is equal to whatever number you came up with, and then say it's always that number, right? There are 2 equivalent ways of thinking about conservation of energy. But sometimes one is more useful. And one of the ways that one is more useful is when we do this plotting of energy thing. So the first question is, why do we want to plot energy? Great question. It's not just to make things more challenging. That's not the point, right? Why do we want to plot energy? Well, there's a couple things. One of them is that, is this one. I want to start in the middle here, because this one's actually going to be make more sense by the end of this lecture. I want to start in the middle here. Sometimes the equation that describes energy is too complicated for us to do direct calculations with. So we're going to introduce this new kind of energy in a little bit. It's potential energy, but the equation is super weird. It's got like something to the 12th in it and something to the 6th in it, and there's fractions, and it's hard, right? And so I have a really weird itch in my nose that's just driving me. I don't know what's going on. Sorry about that. Okay, so there's a 12, something to the 12, something to the 6. There's fractions. It's hard. And so dealing with it, trying to do math with it would be just a pain. And so we're not going to. We are going to just plot it up. And so it's useful for us to be able to plot the energies, because sometimes it's just too hard to work with it mathematically. This is another way of saying a similar thing. Sometimes we are not given enough information to compute the values of each individual energy, right? There are just some cases, and we're going to see some of these cases over the next week or 2, where it's just hard to plot energies, or excuse me, to do the kind of math that we've been doing with energies. And when that's the case, it's better to plot it. And the other reason is we can get other pieces of interesting information from the plot that we can't get other ways, which is we can, for example, figuring out how to use graphs. Not yesterday, but last week. Graphs, you can go from a graph of potential energy to a force, and that's a useful piece of information sometimes. And that means we don't have to do the calculus, right? That's a lot easier. So I'm going to spend some time talking about plotting of energy. And one of the reasons I'm going to do that is that plotting of energy is one of the topics that will be on your quiz next week. So I'll just mention this now. There is a quiz next week. All the practice, I found all the practice problems. They're ready to go. I'll be posting them again, as usual, right after class today. But one of the topics will be plotting of energy. This is a tough topic. Experience in teaching this course. This is a topic that's just people find challenging. And so I want to spend a decent amount of time on it so that hopefully we can be in the best spot possible to succeed next week. So, for example, let's start here. Let's start here with kinetic energy. Let's say we plotted this up. What would it look like? What would the basic shape be? It's a piece. Yeah, parabola, right? That's right. You would look at this and say, well, it's a parabola. There's a v squared in there. It's a parabola, right? I mean, I guess you could plot it in terms of mass, but no, we're not going to do that, right? Mass is just a number that's given to us in the problem. So you plot it with v squared, and you would get something like that looks like this, and you'd be right, basically. But there's one key assumption that we're making that means that this is true. That's not always true. Sorry, the assumption is not always true. And to see that, let's look at this one. This is gravitational potential energy. What does this look like if we plot it? It's just a line, right? Because now we don't have anything squared. We just have height. And we just have height. Gravitational potential energy is the mass times this number g, whatever that is, which is a constant, right? So these two we can sort of think of constants. And then h is changing. So you look at it and you say, well, it's a line. Right? It's a line. And you'd be right, again. But there's another assumption. So now let me ask you a question. What if we wanted to plot gravitational potential energy and kinetic energy on the same plot? On the same plot. So one thing we haven't probably thought a lot about is what's on this horizontal axis right here. So in this case, our horizontal axis was height. And, as expected, the plot was a line. And then in this example, what's on our horizontal axis? It's the speed. And unsurprisingly, because speed is squared in the equation, we get this parabola. But what happens if we want to plot both kinds of energy on a single plot? We cannot put both speed and height on the horizontal axis. I mean, you could do it with a calculator. You could make it, probably a computer. Maybe some really advanced graphing calculators can do this. I don't know. But you could make a three-dimensional plot with a computer. But in general, you can't really do that with just on a sheet of paper. Right? And so, it is correct to say that speed is, or that kinetic energy is a parabola, but only when you have speed here. And it is correct to say that gravitational potential energy is a line, but that's only guaranteed when you have height here. And most of the time, you're going to have something completely different here. And that means that the shapes are going to be looking different. Right? And I want to spend some time going over a problem that you've already seen in DL, but I really want to bring it back to sort of try to hammer some of this home about how we can think about this. So when we're plotting energies, what are we doing? What are we actually doing when we're plotting energies, right? And we're not just drawing random shapes. We're actually providing information, right? So let me give you an example. I might be interested in, let's say you have a car that's driving, and I might be interested in how much kinetic energy it has in terms of how far it's gone, right? I might say, show me how fast the car is moving as a function of where it is, right? Maybe you're interested in the acceleration of the car. And so you're watching the car and you're like, well, when it just gets started, it's not moving, and then when it's over here, it's moving faster, and then when it's over here, it's moving faster, or something like that. That might be a piece of interesting information. I'm trying to think of another good example. You might be watching the flight of an airplane, and you want to know its kinetic energy and its gravitational potential energy in terms of how close it is to its destination or something like that, right? Gravitational potential energy does not depend on how close the plane is to its destination, right? It just depends on its height. And so we get all these cases where we have energies that are not related to the thing that's on a horizontal axis. So here's our first example. This is an example from DL, right? This is the example from DL. On our horizontal, we're interested in what this block is doing as it's moving from left to right. But does gravitational potential energy depend on horizontal position? No, it does not. Does kinetic energy depend on horizontal position? No, it does not. Does thermal energy depend on horizontal position? No, it does not. Right? So none of the energies in our problem actually depend on horizontal position. What we're actually trying to do is get a sense for what the object is doing as it's moving from one place to another. We're trying to get a sense for what the object is doing as it's moving from one place to another. So So how would we go about this? Again, we've seen this, but let's talk about it again. How might we go about this? Well, first, of course, we'd read the problem. And this problem is good because part A is something that you should always do when being given when working with a plotting problem. So there's a block starting from rest, slides down this frictionless slope onto a rough, in other words, not frictionless, horizontal plane. So it's just on the ground here. The initial thermal energy of the block is 10 joules. For some reason, it just has 10 joules of thermal energy here. We don't necessarily know why, but let's not worry about that. The kinetic energy of the block on the rough plane is plotted below the diagram. So this is the kinetic energy while it's on the rough plane. Define y equals 0 at the horizontal plane. Okay. So we did that activity this week where we put y equals 0 in a bunch of different places. We said, what if the floor is actually in the air? Right? In this case, we're using the simplest example where the floor is the floor. And it says, the first thing it says to do is to determine a position where you have enough energy to calculate the total energy. So this is the first step, usually in any plotting problem. We want to know what the total energy of our system is, and then we're going to use the second version of energy conservation to figure out what all the energies look like at a bunch of different places. Okay? So the first thing we want to do is calculate the total energy. Does anybody know where the spot is that we can actually calculate all the energies? Because we're missing a lot of energies here. Yeah? Yeah, question. How much gravitational potential energy does this block have at the top? We don't know. We do not know how much mass this block has. We do not know how tall the slope is. So that's a good thought. That's a really good thought. But we're actually missing information that we need. Is there anywhere else we could? Yeah. Yeah, at 3. What's special about this spot? Well, there's a couple things special about this spot. First, we can figure out what the gravitational potential energy is right there. Right? The block is on the floor. How much gravitational potential energy does it have on the floor? 0. Easy. Kinetic energy is actually given to us there, right? This plot tells us what the kinetic energy is. It's 20. And the problem tells us how much thermal energy the block has. It's 10. Right? So this is an example of a piece of information that's been given, but is a little bit sneaky. This is a frictionless plane. What does that tell, or this is a frictionless slope. What does that tell us about the thermal energy? It's not changing, right? Friction turns kinetic energies into thermal energies. And so if this plane, or excuse me, if this slope has no friction, then there's no change in thermal energy. So as long as the block, when the block reaches the bottom of the slope, it's going to have 0 gravitational potential energy and however much thermal energy it started with. Once it starts sliding along the slope, then its thermal energy will change, but we're not worried about that. And so that tells us that, might have gotten out of order here, that tells us what our total energy is. Right? It's the 20 of kinetic energy that we have here, plus the 10 of thermal energy is equal to 30. And what do we know about the thermal energy in this problem, or excuse me, about the total energy in this problem? It's something that we know about total energies in plotting problems in general, which is that whenever I give you a plotting problem, you can assume that the total energy is going to be not changing. I'm only going to ask you to plot energies for systems where the total energy is conserved. Right? There's no heat. There's no work. There's just energies that are changing. Of course, I just said a few minutes ago that we could describe friction as work. But I also said we could describe it as a change in thermal energy. This is an example where we would choose to use the change in thermal energy, right? Because if we call it a change in thermal energy, then we can just say that energy is conserved, right? There's no energy coming in or out, and do this plotting. Okay, so we now have the total energy. We have the thermal energy for this while the block is on the slope because it's not changing. What might we try to do next? Well, we could do a couple things. We could do gravitational potential energy. That would work. But I want to actually do the rest of the thermal energy. We've already got the thermal energy here. So let's finish it up. And the question is, how do we know what thermal energy looks like in here? We have at first glance, we haven't been given any information that tells us how thermal energy is changing. But secretly, well, not even secretly, but we have, right? This is a system where energy is conserved, yes? So let's think back to the water analogy with 2 cups. Over here, what kinds of energy are we dealing with? What kinds of energy are actually changing in this area on the right? Kinetic energy, obviously. What about gravitational potential energy? Is that changing? No, it's not, because the thing is just on the floor the whole time. So the other one that we have is thermal energy. So all that we have in this case is kinetic energy and thermal energy. Right? We're just pouring water from one cup to the other. So whatever this kinetic energy does, the thermal energy has to do the opposite. Right? This is just conservation of energy again. As I've said, everything in this course is conservation of energy in disguise. Sometimes the disguise is better than other times, but it's just conservation of energy in disguise. We're just doing conservation of energy here, right? Conservation of energy says that when the kinetic energy goes down by a little bit, the thermal energy has to go up by the same amount. And so if this plot kind of swoops downwards, this plot kind of swoops upwards, right? And what is the final state of our system? The final state of our system is it's sitting on the ground, not moving, and all of the kinetic energy it originally had has been converted into thermal energy. And that's what this plot shows. Okay. So now let's deal with the gravitational potential energy. And the kinetic energy in this spot, but we'll start with the gravitational potential energy. Now, in this area, the gravitational potential energy is easy. It's on the ground. The gravitational potential energy is 0. We don't have to think about it. But what about the gravitational potential energy over here? This gets tough. I'm going to show you what it looks like, and then we're going to talk about it. It looks like this. It looks like this. Now, you might be a little bit annoyed at this point because I made this big deal about how gravitational potential energy is not necessarily a line. And then here it is. It's a line, right? But why is it a line? It's not a line because of the gravitational potential energy equation, right? Because gravitational potential energy just doesn't depend on horizontal position, right? It depends on vertical position, right? The gravitational potential energy is a line because of the way that the vertical position depends on horizontal position, right? So this slope is a constant slope. It's just going down, right? And so because of that, when your block has moved, from point 1 to point, let's say the block moves from 0 to 1 and moves down some amount, right? And then you again measure it when the block gets to 2. Because this is a constant slope, the block will have moved down twice as far when it gets to 2 as it had when it got to 1. And it will move 3 times as far when it gets to 3 as it had when it got to 1. And so because the slope looks like this, gravitational potential energy ends up looking like this. But again, this is not necessarily going to be the case. What do you think the gravitational potential energy that? Then the gravitational potential energy would also look like that. Yeah?
Is there any change of kinetic energy in this process?
We're going to talk about kinetic energy in a second. Good thought. All right? So again, it is true that gravitational potential energy is a line, but not because of the equation. It's because of the details of the problem. And so now the obvious question is, what does kinetic energy look like? And this will hopefully really drive the point home that the equations when you're are not as important, right? How would we figure out the kinetic energy in this area? Let's just do energy conservation again, right? The nice thing is the thermal energy is not changing in this area, so we don't really need to worry about it. The gravitational potential energy is decreasing, and energy is conserved. Yeah, exactly. The kinetic energy is just going to increase like this. Why is it going to increase like that? Because it's just doing the opposite thing that the gravitational potential energy is. Just like over here, like this, because it's doing the opposite of what the kinetic energy does, right? We're just exchanging energy. It's the same thing here. The gravitational potential energy goes down like this, and the kinetic energy goes up like that. They're just exchanging energy from the gravitational potential energy to the kinetic energy, right? And so the kinetic energy is not a line. Kinetic energy is not a line. Or excuse me, is a line. It's not a parabola. It's not a parabola. So what have we done? How should we interpret this, right? This plot gives us information about how much energy the block has at all the different points that it travels through. So I might say, well, how much kinetic energy does it have when it's at 0.5, when it's at 5 meters? Well, you go to 5 meters and not very much. Mostly thermal energy, stuff like that. Now again, you might look at this and say, well, this still seems unnecessary because this is the kind of a problem that we could solve with energy interaction, right? So I could say, I could like give you an initial and a final height, and you could figure out the speed of the block at the bottom. You wouldn't have to do any plotting, right? But again, there are going to be some energies that we're only going to be able to work with in plots. And so it's good for us to understand how plots are built so that we can interpret those plots better. And also, like I said, because that is important for certain kinds of energy, it is going to be on your quiz next week. Okay. So, we're done with this for now. And now we're going to move on and talk about this new kind of energy. And I'm going to talk about it for like 10 to 15 minutes, and then we'll be done a little bit early as usual. Okay? Sound good? Okay. So, this is what we're going to start talking about now. And this is the big transition that I was talking about earlier. We're moving into what's called the particle model of matter. What is the particle model of matter? The particle model of matter is exactly this. We are trying to connect the particles to the large-scale behaviors of entire substances. So why are we doing this? So up to this point, right, when we talked about thermal energy and bond energy, they were just sort of energies that were inside the system, right? We did not learn a lot about where they came from or why they were there. It was just that thermal energy is just a kind of energy that an object has because of its temperature. And bond energy is a kind of energy that changes because of its phase, right, when its phase changes, right? And we didn't really say much beyond that. But of course, you know, presumably, at some point in the past, in some science class somewhere, you have learned that, of course, substances are made up of atoms and molecules, right? Substances are not just, I don't know, they're made up of atoms and molecules. And so, if we think about it, and, well, okay, perhaps you've also learned this, maybe you haven't, but perhaps you have, is that if you were to zoom in really close, the things that we think of as temperature and phase and all that actually have to do with what the individual atoms and molecules are doing, right? So maybe, again, maybe you know this, maybe you don't, but if you were to zoom in on some substances, what you would notice immediately is that all of the atoms and molecules in the substance are moving a little bit, even in a solid or liquid, right? In a gas, of course, the gas particles are just flying around doing whatever they want. In a solid or liquid, they're not because they're bonded to their neighbors, but they would certainly be vibrating or something, right? This is just a fact about the way the universe works, is it's pretty much impossible for any tiny thing to stand perfectly still. In fact, it's not pretty much, it is. It is a law of physics that any small thing cannot stand still. And it turns out that that movement turns into what we think about as temperature when we zoom back out again, right? So you zoom in, you see these particles moving back and forth, you zoom out and you see temperature. Let's say you then increase the temperature of your substance and then zoomed in again, the particles would still be moving back and forth, but now they'd be moving faster. And so there is this relationship between the mechanical energies of the particles on one side, right, their kinetic energy and potential energy, which we're going to learn about in a second, and the thermal energy of the particles. We talk about the kinetic energy of a single particle, and then you put a bunch of those together and you get the thermal energy of the substance. We talk about the potential energy of a pair of particles, and then you look at that for all the particles, and you zoom out, and you get what is called bond energy. And so these energies that we've been learning about, these thermal energy and bond energies, are also mechanical energies, just not quite in the same way. Right? They're mechanical energies when you're looking small. They're internal energies when you're looking big. And so our goal over the next couple of weeks is to build some models that explain the connection. We're going to explain the connection between the mechanical energies of the atoms and molecules and the internal energies of the substance that they create. And the big idea that's going to allow us to do this is this, which is a little bit scary. So this is called the Lennard-Jones potential. I'm going to talk about what it is and why we use it in a minute. But I first things first want to point out the ways in which it is exactly the same as a bunch of stuff we've already seen. There are a few. So what is this? Well, I call it the Lennard-Jones potential, but that's short for something, and that is short for potential energy. So this is a potential energy, right? This is not the first potential energy that we've seen. We've seen spring potential energy and gravitational potential energy. Why is it so important that this is a potential energy? Because everything that we already know about potential energy applies. In that sense, it is a new potential energy. It is maybe different from anything we've seen before, but it is still just a potential energy. And what I mean by just a potential energy is that, again, anything we know about potential energy, and therefore anything we know about energy generally, applies to this energy as well. It applies to this energy as well. So for example, let's say I wanted to know what the force was right here. I wanted to know what force was being felt by an object in this potential energy when that object was right here. You could tell me, because you know how force and potential energy are related, that the force would be that way, because that's the way that causes the potential energy to go down. Right? That's just a fact we learned about potential energy. It applies to this potential energy just like it applies to the spring potential energy, just like it applies to gravitational potential energy. Right? Energy conservation also applies, which means that if you were asking what the kinetic energy of what, we don't even know what we're talking about when we're talking about this thing, but if I wanted to know what the kinetic energy is, I could look at this and say, well, as the object moves this way, its kinetic energy would be going up because its potential energy would be going down. That's what energy conservation tells us. And so in many, many ways, this is just another energy, just like all the ones we've seen before. But then there are some ways in which it's not. There are some things that make it unique. So to understand that, let's talk about what we actually use it for. What we use it for is if you have a pair of neutral particles. So these are particles that are not electrically charged. Now, we're not going to talk about positive and negative electric charges a lot in this course. We'll mention it very briefly in one DL activity. But we're not going to be talking about it, certainly not testing on any of that stuff. You will learn a little bit more about it in Physics 7c if you take Physics 7c. But for now, if you have two particles that are sitting next to each other that do not have an electric charge, the energy that we're going to use to describe the way they interact with each other is going to be this one. The energy that we use to describe the way that they interact with each other is going to be this one, right? So with that said, let's go back and think about some of the stuff I talked about. So again, what would it mean to say that we're here again, we're looking at this plot, and we want to know what the particles are going to do if we hold them here and then let them go. Well, they're going to feel a force this way, right? They're going to feel a force that way. What does that mean in this context? It means a force that pulls the particles together. Why does the universe work this way? That's just the way it does. For some reason, this is the way it works. So this is an energy that describes how two particles that are next to each other are going to interact, right? That's the idea. Now, there are some things that make it a little bit weirder. And the two main things there are the axes. So let's start with this one. So this axis is potential energy. Okay, that makes sense. This is a potential energy. But notice this thing in parentheses. It says, in units of well depth. Okay, well, what is that? Why am I not just giving you a number, right, and saying this is 10 to the negative 20 joules or something like that. Why am I not just giving you a number? And the answer is that different particles behave different ways. Some particles have very strong bonds with a lot of energy that hold them there. Some particles have very weak bonds that are very easy to break, right? We do not want to have to draw a different Lennard-Jones potential energy plot for every single kind of particles that we could get. That would be a pain. That would be a real pain. And so we don't want to do that. So what do we do instead? We just say we're just going to draw one plot. And then if you need the actual amount of energy, we'll give it to you. Right? So for example, what does this negative 1 mean? What does this negative 1 mean? It means negative 1 times whatever epsilon is, which again is just a number. It's just an energy. What does negative 0.6 mean here? It means negative 0.6 times whatever the well depth is. Right? On the horizontal axis here, right? We're saying the distance between the centers of the atoms or molecules, the distance between the center of the atoms or molecules in units of the particle diameter, sigma. And it's the exact same thing. Different particles have different diameters. Really, really big particles are going to be farther apart than really, really small particles. We don't want to draw a different plot for every different kind of particle that we could get. And so instead, it's the exact same thing. What does 1 on this plot mean? It's not an actual distance. It just means 1 times whatever the diameter of the particles is, which would be just a number in meters. I might 3 times 10 to the negative 10 meters, something like that. Right? What is 2? It means 2 times whatever the diameter of the particles is. That's the weirdness about this plot, but again, I want to go back and say that this is just a potential energy, and everything you know about potential energy still applies here. This is sort of summing the stuff that I said. These slides are posted, so you're welcome to write this down now or just go check for it. There is one thing I didn't mention, is there's this thing called the equilibrium distance. Why is it called the equilibrium distance? Well, I'll tell you where it is, and maybe we can think about why it's called the equilibrium distance. This is that location right here. Why do we think this is called the equilibrium distance? What does this part kind of look like? It sort of looks like a spring, right? It sort of looks like a spring. And this is, what would the force be if we put the particles right here? What would the force be? There'd be no force, right? Because there's no slope here. It's flat. And if you put the particles, if you could perfectly place the particles with the tiniest pair of tweezers ever, right where in that spot, they would just sit there and never move. That's sort of where they want to be naturally, right? Just like a spring has a natural length, the bond between a pair of particles has a natural length that it wants to be. Now, in practice, this is not going to be the case. Let's say the particles were here, and we gave them a little kick that way. Right? What are they going to do? They're going to start going up here, and then they're going to turn around and they're going to fall back in. They're going to behave just like a spring that bounces back and forth. And so in a lot of ways, this quote-unquote equilibrium distance is exactly like the equilibrium length of a spring. Right? Now, of course, this bond is not a spring. It certainly looks nothing like a spring as we get out here. But certainly near there, it looks quite a bit like a spring. And so we call this distance the equilibrium distance. It is the length that the bond wants to be naturally. It's not necessarily the length that the bond is at any point in time, but it is the length the bond wants to be. So this is not the right phrasing. I should not have said this. The equilibrium distance does not describe how far apart the particles necessarily are. It describes how far apart the particles sort of want to be. And it's always equal to the same number. 1.12 times the particle diameter. Okay. So, last thing I want to say. This looks familiar. We already did it once. It's a problem a lot like it. We have a total energy. We have a potential energy. And we want a kinetic energy. How would we get it? We would do the same thing that we did when we had a potential energy and a total energy and we wanted a kinetic energy before. We would just compare. I'm not going to talk a lot about what I'm going to show, this next slide that I'm going to show, or the actual plot of the kinetic energy, because you're going to do this exact activity in DL this week. Okay? So I'm not going to spend a ton of time belaboring it. This is what it looks like. There are some tricks that you're going to learn about in DL. But why does the kinetic energy graph look like this? It looks like this because it's just doing the opposite of what the potential energy graph is doing, right? The potential goes down, the kinetic energy must go up. When the kinetic energy, or when the potential energy goes up, the kinetic energy must go down, right? It's still energy conservation, right? Now we're talking about something completely different than anything we've looked at before. We're looking at these little tiny particles, atoms and molecules, stuff that we can't see with our naked eye. We have no real intuition necessarily for how they work. But what we know about energy still applies here, right? This is a system where energy is conserved. And that means if one kinetic energy, or if one type of energy is going down, the other one must be going up. We're pouring water from one cup to another. We're not emptying the cup onto the floor or pouring more water into it from the tap. Okay? And that is the reason that we spend so much time on this, because we are now going to be entering into a phase of the course where the systems that we're going to be dealing with, like particles, is not something we have a ton of intuition for. Right? Again, what's an example of something we have intuition for? If I drop this, it falls. I don't have to tell you that. Right? We have some intuition for that. Right? But by starting with stuff that we have intuition for, and learning to understand energy, how it works in systems where we do have intuition, we can now apply it to systems where we have less intuition. Right? It is not as obvious to me how particles behave or why they behave that way, but I do know a few things about energy. And all the things I know about energy that I learned for kinetic energy, gravitational potential energy, all that stuff, still applies when we talk about small things. And if we can remember that, it's going to make everything we do from here on out in this course a lot easier. All right? Okay. Thank you all for being here. Have a great rest of your week. I will see you next Monday. Or later today in my office hour if you happen to stop.